Hello, I'm Marina Aoyama from the University of Edinburgh. I'll be presenting my recent work on future learning of force-based motions from demonstration through pre-training of haptic representation. Our aim is to enable robots to learn to manipulate objects with different physical properties from a small number of demonstrations. In the problem we consider, the robot performs exploratory actions to identify physical properties of the manipulated object. Given the force trajectory observed during exploration, the robot generates motions for the target task. Our learning objective is to minimize the error between the motion trajectory demonstrated by humans and that generated by the model. For training, we have two types of dataset: unsupervised haptic data and demonstration data. The unsupervised haptic data consists of force trajectories autonomously collected by performing predefined exploratory actions on various objects. The demonstration data consists of pairs of a force trajectory obtained through exploration and corresponding motion trajectory demonstrated by an expert performing the target task. We have access to a significantly larger number of unsupervised data than human demonstration data. To address the issue of existing learning from demonstration approaches that suffer from limited generalization with few demonstrations, we propose a semi-supervised learning from demonstration approach. The idea is to decouple the haptic representation encoder, which encodes force observations into physical properties of an object, from the motion generation decoder, which maps the encoded object properties to the desired behavior. This enables us to pre-train the haptic representation using a large amount of unsupervised haptic data. Therefore, the proposed approach consists of two training steps. In the first step, we train a haptic representation encoder-decoder using unsupervised data by minimizing the reconstruction loss of the force trajectory obtained from exploration. The objective is to capture the underlying distribution of object properties rather than generating the desired motion for the target task. Then, we freeze the weights of the haptic encoder and train the motion generation decoder by minimizing the mean squared error between the generated and demonstrated motion trajectory. At test time, the robot first performs the same exploratory actions used in training to encode the properties of the object to be manipulated. Then it generates and plays back the desired motion accordingly. In our experiment, we use a wiping task as an example of a force-based manipulation task, as the desired wiping motion depends on the physical properties of the sponge. We use Pi palette for simulated data collection and KUKA-EVA robotic arm as physical robot setup. During exploration, we record force and torque in the X, Y, and Z directions for 200 time steps for each exploratory action. We collected unsupervised data in simulation using two exploratory actions, pressing and lateral motion, with objects of varying stiffness and surface friction. For demonstration data collection, the robot starts by autonomously performing the two exploratory actions. And then the human demonstrator provides the desired motion for the target task. During task demonstration, we record the end effector position in X, Y, and Z directions for 2000 time steps. In this wiping task, the desired behavior is to apply as much force as possible in the normal direction while maintaining a smooth motion. Thus, the demonstrator applies larger forces for compliant and smooth sponges and smaller forces for stiff and rough sponges. In our experiment, we observed a significant reduction in the root mean squared error of the generated wiping motion trajectory where we pre-trained the model using 1000 unsupervised haptic data compared to we only use demonstration data for training in all 4 test cases of stiffness and friction, interpolation, and extrapolation. Here is an example of the generated wiping motions for an unseen compliant sponge with and without pre-training of haptic representation. The pre-trained model successfully applies a greater force closely capturing the desired motion. For the case of an unseen stiff and rough sponge, the model without pre-training fails to generalize the desired motion for more compliant and smoother sponges and counters drain training, leading to extremely high forces and a non-smooth circular pattern. Finally, we visualize and analyze how the haptic encoder captures the properties of real objects in its latent space. We can see that the latent space is self-organized with respect to the stiffness and surface friction of the sponges when we pre-train the haptic encoder on simulated unsupervised haptic data and evaluated it on real sponges, while the latent space shows a lack of clear organization when the model is trained only on demonstration data. Furthermore, when the robot performs pressing only, the latent space clearly captures the stiffness of the sponges but not the surface friction, and vice versa when performing the lateral motion only, indicating that the haptic encoder encodes meaningful information from each exploratory action without explicitly providing the levels of the physical properties. In summary, we propose decoupling of the haptic representation encoder from the motion generation decoder, enabling us to utilize a large amount of unsupervised data. We show that our approach can achieve force profiles close to human demonstration for unseen objects on a physical robot setup and validated that the haptic representation encoder pre-trained in simulation distinguishes the physical properties of real objects, leading to improved generalization in few-shot learning from demonstration. Thank you for watching.